In this video, we're going to study how we can use integrals to calculate probability. Okay. Well, first, what is a probability? Well, it's simply a number between 0 and 1 that measures the likelihood of some event occurring. A probability of 0 means that the event is impossible. A probability of 1 means that the event is guaranteed. So these are best described as an area under the graph of a function which we call the probability density function. Two types of probability density functions. We have discrete and we have continuous. All right, so for purposes of this video, we're only going to be looking at continuous densities. Now, in probability theory, capital X is used to represent the phenomenon we are analyzing. And we call this a random variable. Probability that X lies in a given range, let's call that range A to B, is denoted this. Now we say that P, little p, is a probability density function for a random variable X if it is continuous such that the probability that X falls between A and B is equal to the integral from A to B, little p of X dx. Right. Suppose that a probability density function little p has domain I and that this domain contains all possible values for x. Note that it is, of course, possible for this interval to be infinite. So P has to satisfy two conditions. First, P of x has to be greater than or equal to 0 for all x and I. Second, if we integrate P of x over the entire interval, we must get 1. As an example, what we're going to do is find a constant c for which P of x equals c over x squared plus 1 is a probability density function, which I'm going to shorthand as PDF, with domain minus infinity to plus infinity. Then we will compute probability that x lies between 1 and 4. All right, well, the first condition satisfied. Oh, I'm sorry. Two conditions that have to be satisfied, right? First, integrating over the entire thing must give us 1. Second, it has to be greater than or equal to 0. Right, so to satisfy the first condition, c would have to be greater than or equal to 0, right? X squared plus 1 will always be positive. So let's first look at the integral over its domain of P of x dx. So this will be the integral from minus infinity to positive infinity, c over x squared plus 1 dx. C is a constant, we factor it out. That has to equal 1. Which means, by the way, that c would have to be 1 over this integral. So let's go ahead and calculate that integral. Right, so we're going to have to split this into two integrals and take limits. So we're going to have the limit as a approaches negative infinity of the integral from a to 0. Then plus the limit as b approaches positive infinity of the integral from 0 to b. We're going to have the inverse tangent function, right? So this will be inverse tangent of x. X goes a to 0. Right, and then, of course, same thing, except now x goes from 0 to b. Right? Now, if we look at the inverse tangent of 0, that is just simply 0. So what we have is the limit as a approaches negative infinity. Right, negative inverse tangent of a plus the limit as b approaches positive infinity of inverse tangent of b. That first limit is negative pi over 2. That second limit is positive pi over 2. So we find that this limit, these limits add up together to be pi, so the integral converges to pi. And therefore we can conclude that c has to be 1 over pi. Now for the second part, notice that this would mean that little p of x is equal to 1 over pi divided by x squared plus 1. Which of course means that if we take the probability that x is between 1 and 4, we have the integral from 1 to 4 of 1 over pi over x squared plus 1 dx. This gives us 1 over pi times the inverse tangent of x. X goes from 1 to 4. So inverse tangent of 4 inverse tangent of 1 all over pi. And if we take a look, and come over to our calculator, we get 0.1720. Typically, we'll keep probabilities to 4 decimal places. So average value, also known as the mean, of a random variable is defined as mu or e of capital X, which is the integral over its domain of x times little p of x dx. There are several special types of probability distributions. One such is known as the exponential distribution. It has a density function, P of t, equal to 1 over r e to the negative t over r, where r is larger than 0 and t is between 0 and infinity. This type of distribution is commonly used in the modeling of wait times between events that occur randomly. We're going to look at the mean of the exponential distribution. So we have mu is equal to the integral over I of t times p of t dt, right? So we get the integral from 0 to infinity, t over r, e to the negative t over r dt. Right. Now, let's use a u substitution. I'm going to change a variable. Specifically, we're going to use... I'm sorry, no, we're not going to do that. What we're going to do is we're going to write this as 1 over r times the integral from 0 to infinity, t e to the negative t over r. All right, this is going to be an integration by parts. But first, let's go ahead and take limits, right? So if we just look at this, right, then use the integration by parts. U t dv e to the negative t over r. Right, this, of course, means that du is simply dt, and v is negative r e to the negative t over r. So we get the limit now as b approaches infinity, right, of negative tre to the negative t over r, evaluated from t goes 0 to b, minus the integral from v du, so we get plus r times the integral 0 to b. Of e to the negative t over r dt. And if we now evaluate this from 0 to b, we're going to get what? Negative b r e to the negative b over r, then plus 0, right? So that's that piece evaluated. Now let's evaluate this second integral, okay? That'll give us minus r squared e to the negative t over r. Right, now evaluate that, we're going to get minus r squared e to the negative b over r minus negative plus r squared. Right, now these limits, That term goes to 0. That term goes to 0. We are simply left with r squared. So our average value, right, we said is 1 over r times this integral. So we get 1 over r times r squared, which is just simply r. So the variable r in our probability density function for an exponential distribution is just the average wait time. As an example, what we're going to do is look at drive-through fast food restaurants, and we're told the waiting time, we're going to use this capital T, between customer arrivals at some fast food restaurant drive-through is a random variable with exponential distribution. If the average wait time is 60 seconds, we are asked, what is the probability that a customer will arrive within 30 to 45 seconds of another customer. Well, the first thing we want to do is write out our model, right? So our density function, P of t, is e to the negative t over 60 divided by 60. Right, where t can go from 0 to infinity, right? Because remember, we said that the density function is 1 over r, e to the negative t over r, where r wound up being our average. What this means then is that the probability that t will be between 30 and 45 seconds is the integral from 30 to 45 e to the negative t over 60 divided by 60 dt. This is going to equal negative e to the negative t over 60 evaluated. T goes from 30 to 45. Right, so this is e to negative 45 over 60 minus e. I'm sorry, it's negatives. So it should be negative e to the negative 45 over 60 plus e to the negative 30 over 60. Right, we want to find an approximation to this. get about 0.1342. Now, one of the most common types of distribution is the normal distribution. This has a density function. P of x equals 1 over sigma times the square root of 2 pi e to the negative x minus mu squared all over 2 times sigma squared. Where x can go from minus infinity to positive infinity. Here, sigma represents the standard deviation, and mu represents the mean. A normal distribution with mean of 0 and standard deviation of 1 is called a standard normal distribution. Obviously, this is going to have a density function, P of x, equal to 1 over the square root of 2 pi e to the negative x squared over 2. And again, x can go from positive infinity to negative infinity. Right. Now, if we wanted to find the probability that a normally distributed random variable x falls between values a and b, right, we would have the integral from a to b, 1 over sigma times the square root of 2 pi e to the negative x minus mu squared over 2 sigma squared dx. Obviously, sigma and square root of 2 pi are constants, so we can factor that out, and this is what we're left with. Notice that this integral has no analytic solution. Now, what we can do is define a function. Call it f of z, which is 1 over the square root of 2 pi times the integral from minus infinity to z e to the negative x squared over 2 dx. Notice this also has no analytic solution. However, this function leads to the idea of the z-score which you may have studied if you took an elementary stat course. Also, generally speaking, this integral is easier to solve numerically than this integral. Now, if x has a normal distribution with a mean of mu and standard deviation sigma, then for all a less than or equal to b, we have the following. The probability that x is less than or equal to b is equal to big F of b minus mu divided by sigma, and the probability of a being less than or equal to x less than or equal to b is equal to big F of b minus mu over sigma minus big F of a minus mu over sigma. This is a relatively simple proof. We make use of two change of variables. The first is u equals x minus mu, and then we say t is equal to u over sigma. Notice by doing that, here's what we're going to get. Probability that x is less than or equal to b, which is 1 over sigma times the square root of 2 pi, integral from minus infinity to b of e to the negative x minus mu squared over 2 dx. Using the first substitution, we get 1 over sigma root 2 pi, integral from minus infinity to b minus mu e to the negative u squared over 2 sigma squared du. Now, using the second substitution, we get 1 over the square root of 2 pi times the integral from negative infinity to b minus mu over sigma e to the negative t squared over 2 dt. And notice that this is precisely the definition of f of b minus mu over sigma. Now, the second formula. Follows from the fact that this probability represents an area between A and B, which is given by f of b minus mu over sigma minus f of a minus mu over sigma. For example, we're going to assume that the scores represented by the random variable x on a standardized test are normally distributed with a mean of 500 and standard deviation of 100. We want to find the probability that a test chosen at random has score at most 600 and then between 450 and 650. So we'll go ahead and use Simpson's rule. First, probability that x is less than or equal to 600. Right? So we get 1 over 100 square root of 2 pi times the integral negative infinity to 600 of e to the negative x minus mu, which is 500, squared, all over 100. I'm sorry, 2 times 100 squared dx. Right, so notice that if we look at our distribution, right, our normal distribution, which is a bell curve, this is the mean, which is 500. Okay. Let's say this represents 600, right? So the area we're trying to find is this area. So what we can do is split this probability up. We'll have the integral from negative infinity to 500 and then plus this from 500 to 600. But this term is the probability of being less than the mean. That is automatically 0.5. So all we have to do is calculate this integral using Simpson's rule. All right, so let's come over here. All right, so let's define our delta x of n. B minus a divided by n, right? Then we define our Simpson's function. 1/3 times delta x of n times then f of a plus f of b plus 4 times sum j equals 1 to n over 2 f of a plus j 2j minus 1 times delta x of n plus 2 times probability j equals 1 to n over 2 minus 1 f of a plus 2j times delta x of n. Now let's go ahead and define our function, right? It was 1 divided by 100 times square root 2 times pi times e raised to the negative x minus 500 squared divided by 2 times 100 squared. A, we were starting at 500 for this integral, right? And we were ending at 600. Now let's just start calculating. Let's start with Simpson's rule of 4. Now let's look at 6. Remember, we want 4 decimal places. Oh, good. They agree to 4 decimal places. So 0.5 plus, we had 0.3413. I should say this is approximately, right? It's not equal. So we get about 0.8413 as our probability. For x between 450 and 650, what we have, 1 over 100 square root of 2 pi times the integral from 450 to 650 e to the negative x minus 500 squared all over 2 times 100 squared dx. So again, we're going to use a calculator. Right? Our f is the same. The only thing that's now going to change is our a and our b. So let's redefine a to be 450. Let's redefine b to be 650. Now let's do Simpson's rule for n equals 4. Simpson's rule for n equals 6. They do not agree to 4 decimal places. Let's look at 8. They still don't agree to 4 decimal places. So let's look at 10. They now agree to 4 decimal places, and we get 0.6247.